Hi guys, welcome to Mini Talk in Chemistry. Today we will discuss about another transformation for making carbon sp2 heteroatom bond, a fascinating motif often seen in pharmaceuticals, named Chan-Lam coupling reaction, also known as the Chan-Evans-Lam coupling reaction. We'll start by reviewing their work published in 1998 before looking at an example in photosynthesis of isodityrosine. After that, we examine the mechanism of the reaction and the formation of side products. As usual, we will finish with the extension of the scope and some general reaction conditions. This reaction is unique, coupling two nucleophiles, an aryl organoboron compound, and an amine or phenol using copper-2 acetate under air. Now let's go back to 1998 when Chan, Evans, and Lam published their work back-to-back in tetrahedron letters. Chan and his co-workers reported the C-aryl N bond and C-aryl O bond formation by simply stirring an amine or phenol with an aryl boronic acid with stoichiometric amount of copper-2 acetate and triethylamine or pyridine as the base and methylene chloride at room temperature under air for 1 to 3 days to give the amine or diaryl ether in good use. In the same fashion, Evans' group published the formation of diaryl ether, while their work focused on the optimization of the reaction condition. The addition of powder 4 angstrom molecular sieves to the reaction mixture increased the product use by suppressing the formation of byproducts such as phenol and diphenyl ether, which are detected by GCMS. According to their studies, copper-2 acetate was the optimal copper-2 source, dichloromethane was the optimal solvent, and 5 equivalents of amine base were optimal. Moreover, reaction was better in the presence of oxygen. In addition to this work, Lam's group published a beautiful cross-coupling reaction between aryl boronic acid and a variety of NH-containing heteroarine. Many groups then utilized this methodology in the synthesis of biologically active molecules and natural, for example, an efficient conversion photosynthesis of isodityrosine were developed from two natural aromatic amino acids, L-tyrosine and L-phenylalanine. Because of the minus of the reaction condition on the sterol center was preserved. Due to the instability of the copper intermediates, the complicated interaction with the boronic acid, it has been challenging to elucidating the mechanism. To make it short, the reaction process via coordination of heteroatom species and a transmetallation of acid boronic on the copper salt, giving a copper-2 complex, which is oxidized to a copper-3 complex. The copper-3 aryl alkoxide or copper-3 aryl amine intermediate undergo reductive elimination to give aryl ether or aryl amine. The reductive elimination from the copper-3 species is faster than from the copper-2 species. You can have a look in this publication for more information about the mechanism which are described as catalytic cycle for esterification and for amination reaction. Besides, you can find a study about the side products. Several side products were identified including proto-deboronation product, oxidation product, oxidative homocoupling product. Proto-deboronation were comparable to amination, while competing oxidation delivered phenol. As phenol increased, competing copper catalyzed esterification delivered the oxidative homocoupling product. Under especially dry conditions, the quantity of phenol and oxidative homocoupling can be lowered significantly, and homocoupling of the organoboron component can be observed, giving 6% of tetraphenyl. The change in stoichiometric amount between boronic acid and amine was found to be effective in reducing the side products formation and increasing the reaction reaction yield. The cross-coupling reaction between aryl was more difficult than the corresponding boronic acid, yielding only 28% yield instead of 87%. Pepin reactivity issues in the Chan-Evans-Lam coupling reaction are due to catalyst inhibition of the pinnacle. Based on the result of the mechanistic study, the conventional organic-based triethylamine were replaced directly by boric acid. The boric acid forms stable boric acid ester with pinnacle, rendering a good yield for the coupling reaction with aryl pepin. Aside from copper-2 acetate, which is the most frequently used catalyst in Chan-Lam coupling reaction, all the copper-2 salts or copper-1 halide could be used, such as copper triflate, copper sulfate, copper chloride, copper bromide. As an alternative to copper, nickel chloride or nickel acetate could be also effective for Chan-Evans-Lam cross-coupling reaction. Due to the nature of the reaction, often even require air as oxidant, the Chan-Evans-Lam cross-coupling reaction has proven to tolerate air and moisture. Evans Group mentioned that a dry, pure oxygen atmosphere were unnecessary, and Lam's group stated that the bubbling of oxygen during the reaction gives no improvement in yield. Ligand, base, and additive can be added to reduce the reaction time. The reaction is tolerant to a wide range of solvents such as dichloromethan, acetonitrile, dioxane, etc. In terms of nucleophiles, the Chan-Evans-Lam coupling reaction had a broad scope. By now, the scope of the reaction includes many other heteroatoms besides nitrogen and oxygen. The boronic acid could be replaced by other organometalloids such as stannate, silane, zinc, or magnesium. To conclude, the copper catalysts are abundant, cheap, and mild condition, making the Chan-Evans-Lam coupling reaction appealing toward the Bergwald-Hartwig and the Ullmann cross-coupling reaction. The Chan-Lam carbon heteroatom bond cross-coupling reaction is complementary to the Suzuki-Miura carbon-carbon bond cross-coupling reaction. Thank you for watching and see you next time.